Welcome back to The Explainer. We are jumping right in today to finish up your operational vocabulary for a Zippa-pod propulsion. We're going to look closely at the physical and computational differences behind bridge commands that you absolutely need to know. So let's get right to it. Okay, so last time you'll remember we covered the critical safety restrictions of a Zimmermann mode, where power is automatically restricted to protect the berth, and we contrasted that with the wide open power but restricted steering angles of cruise mode. But now we need to ask what actually happens when a bridge officer is actively maneuvering near a really tight berth and suddenly needs much faster response times. Section 1. Fast steering. Speed versus torque. All right, this brings us to the very first dilemma in the officer's toolkit. When you activate fast steering, you gain crucial rotational speed. The system basically switches to a sustained hydraulic configuration that is a whole lot faster than normal, usually by running multiple hydraulic winch motors in parallel. This is literally a game changer for those tricky near-alongside maneuvers. But you do sacrifice something pretty major in return. You get reduced available steering torque against the sea, so it's essentially a calculated trade. You're swapping raw physical holding strength for rapid agility. Section 2. Control logic. NFU versus FU. Now that we've got a handle on the physical mechanics, let's talk about the digital command logic. The first philosophy here is non-follow-up, or NFU. Think of this as fundamentally an open-loop system. As the operator, you directly command a general direction, like, say, pressing and holding a steer port button. There's absolutely no absolute target feedback being processed by the system's logic here. The pod just keeps rotating in that direction for exactly as long as you hold the command, and it stops the second you let go. It's direct, it's manual, and it's totally open-ended. In strict contrast to that, we have follow-up, or FU control. Now this one is closed loop. Instead of just commanding a general direction, you input an absolute, specific target value. So, for example, you might dial a helm to exactly 20 degrees port. And once you set that value, the automation totally takes over. The internal control loops work together to automatically ramp the azipod right to that precise target angle and then hold it there. You basically give it the destination, and the machine figures out the journey. Let's lock this concept in with a quick check, because knowing this instantly is absolutely vital on the bridge. Imagine you're at the helm. You issue a specific command. Steer 15 degrees starboard, and you fully expect the pod to automatically stop exactly at that 15-degree mark without you doing anything else. Which philosophy are you using here? Take a second and think about it. Did you guess FU? Because it's follow-up control. The really crucial point here is that combining an absolute target value with an automatic ramp to that exact value, well, that's the defining behavior of closed-loop follow-up control. If this were NFU, you'd just be holding a lever to starboard, staring at the rudder angle indicator until it hit 15, and then manually letting go. That closed-loop automation is exactly what makes it follow-up. Section 3. The reverse power phenomenon. This phenomenon builds into the massive physical interaction between the hull, the propeller, and the ocean itself. Reverse power happens when a ship is traveling so fast, say during a crash stop or a really rapid deceleration, that the ship's physical speed actually exceeds the speed the propeller is being driven at. And when this happens, the sea physically drags the propeller blades. The kinetic energy of the ship moving through the water literally forces the propeller to turn. That effectively turns the massive electric azipod motor into a generator, sending megawatts of power backward, directly into the ship's grid. You might have come into this explainer pair with zero formal azipod vocabulary, but just look at what you command now. You've got the complete glossary down. The azipod room for emergency control, the automatic safety limits of Aziman, the wide-open parameters of cruise mode, the hydraulic trade-offs of fast steering, the computational differences between open-loop NFU and closed-loop FU, and of course, the mechanical reality of reverse power. This is exactly the terminology that every single bridge and engineering officer relies on to communicate safely and effectively out there. So, now that you command the bridge terminology, we really have to look inside the pod itself. Think about it. We have this multi-ton unit spinning underwater, generating massive thrust, and even acting as a generator during reverse power. It really makes you wonder, right? What exact kind of mechanical engineering can possibly withstand the crushing, violent pressure of the ocean, all while keeping highly sensitive internal electronics perfectly dry? We're going to uncover that incredibly engineered, layered defense in our next explainer. See you then.